In this video, you're going to learn everything you need to know about forces in a thorough yet concise overview. As a 19th year physics teacher, I've distilled all the main ideas of forces into 6 major chunks so that you're able to learn them in 45 minutes. For the second portion of the video, we spent 18 minutes taking a look at 2 force problems in detail to learn all the strategies necessary to be successful. We're going to be taking a look at Newton's first law and third law to begin with. We're going to leave out the second law because that has a lot more problem solving in it. Then we're going to develop the concepts of all the different types of forces and how to draw our diagrams. And then from there, we're moving on to Newton's second law, which brings up a lot of the problem solving and taking a look at those strategies. From there, there's a lot of classic problems and ideas that are related to angles, inclines, and pulleys. So we're going to be taking a look at a lot of those specific problems and the approach you want to take to them. Then we're going to take a look at Hooke's law and springs for a small portion of the video. And then at the end, we're going to be connecting some kinematics with dynamics conceptually and mathematically as well. So let's get started with taking a look at Newton's first and third law. So let's go ahead and start off with Newton's first law. So Newton's first law is also known as the law of inertia, and it states an object will remain in its state of motion unless an unbalanced force acts on it. And its state of motion is going to be one or two things. It's either going to be in motion, which means it is moving at a constant velocity, or it is motionless, which means it's at rest. Okay, and acceleration wouldn't be considered in a state of motion because if it's accelerating, that means it's speeding up or slowing down. So that means it is changing its state of motion because an unbalanced force is acting on it. So the original states of motion are basically in motion or motionless. Now, one thing that we want to make sure we're aware of is what inertia means. Inertia is a property of all masses that describes its tendency to remain in its state of motion. And the indicator for if something has more or less inertia is its mass in kilograms. So it's safe to say if something has 2 kilograms as opposed to 1, it definitely has more inertia, it has more tendency to remain in motion or remain motionless. So let's take a look at a couple of examples of Newton's first law to make sure we know how to apply this concept to some different scenarios. Now, say for example, you are moving in a car and the car is traveling forward at 30 miles per hour. And if the car is going forward at 30 miles per hour, that means it and everything in it is moving about 30 miles per hour, assuming that everything is at rest relative to the interior of the car. Now, what happens is if the car brakes abruptly, then the person is going to feel like a force is pushing them forward to the front of the car. Now, with Newton's first law, a lot of times it's actually a lack of force that causes that feeling. So if you're going 30 miles per hour and the brakes are abruptly hit, then it would feel as if you were getting pushed forward, but you're not. You're remaining in your state of motion. So the person wants to continue moving at 30 miles per hour, and they do briefly. And then now the car has actually slowed down. So the car is actually going slower than the person. Therefore, the person would move forward in the car. So because of a lack of force until probably the seatbelt tugs on you, you're going to feel yourself being thrown forward. So that is one example of Newton's first law. Just like if you are sitting at rest and the car speeds up very quickly, it feels like you're being pushed backwards because you remain at rest as the car moves forward more quickly and sort of moves without you temporarily. And that delay between your movement and the car's movement is what you feel as a force pushing you back, although there is no force actually pushing you back. So let's go ahead and take a look at one more car example. And say, for example, this is the top view of a car, and it's going forward, and then it turns to the right. Now, if it turns towards the right, then the car is going to start to get angled like this. And if you imagine someone turning the car really sharply to the right, you're going to feel like you're pushed to the left. But in reality, if you are going forward to begin with, you want to remain at a constant velocity. And a constant velocity means two things. It means you're going the same speed and direction, because velocity has a direction. So if you were going forward at, we'll say, 20 miles per hour, and then the car turns right, it's kind of like it's moving without you. And now if you are continuing on that straight path, you are going to start to bump into the left side of the door, and it's going to give you that feeling that you're being pushed to the left. Again, there isn't any force pushing you to the left. It's everything moving to the right to give you the sort of the illusion that you're being pushed over to the left. All right, so that's basically Newton's first law. Has a lot to do with inertia. And again, inertia is just solely based on mass. So if something has more or less mass, it has more or less tendency to keep on moving or stay at rest. A lot of these scenarios are related to things that are in something else, like a person in a car was the example that I went with. All right, so let's go ahead and move along to Newton's third law. So for Newton's third law, it's every force has an equal and opposite force, and all forces come in pairs. So a lot of times Newton's third law might be stated as every action has an equal and opposite reaction. That version of Newton's third law I don't particularly like, because it sounds like something is happening and then something is happening as a reaction right after, when in fact they're happening simultaneously. So if a person is pushing on an object, we'll say like they're pushing on a big box or a crate, they apply a certain amount of force, and we'll say maybe they're applying 10 newtons of force this way on the box by the person. There is for sure an equal and opposite force in every single case. The box is then pushing back on the person with 10 newtons of force in the exact opposite direction, and this is on the person by the box. Okay, now a common thing that people may ask is, well, if every force has an equal and opposite force, and if you have 10 newtons going to the right and then 10 newtons going to the left, why aren't they canceling each other out? That's because they're on different objects. So if you analyze just the crate itself, and this is these are some ideas that we're going to get to in a moment here with our force diagrams, but we have the force of gravity from the earth pulling the box down. We have something called the normal force, which is the ground supporting the box. And then we most likely have some force of friction going to the left. We'll call that kinetic friction, FFK, which is based on the roughness of the surfaces. So as long as that 10 newtons is enough to overcome the force of friction, then it can be moved. Now, this 10 newtons isn't actually acting on the box itself, so it wouldn't be included with your force diagram on the box. If you drew a force diagram on the person, then it would be involved. So if we're only taking a look at the things on the box, then we have Fn. We have this 10 newtons from the person, which we'd probably call an applied force. We have force of gravity and then the force of kinetic friction. So this 10 in green is not on the box, therefore it wouldn't be a factor in canceling out this red force over here, 10 newtons to the right. All right, now with Newton's third law, there's a few different applications to it. So there isn't any case where this isn't true. So the word every means that in every single case, there is another force that is exactly the same number, opposite directions. That's where it says all force comes in pairs. A couple other famous examples would be maybe something like a rocket blasting off And that is a terrible rocket, but um, if a rocket pushes the gas out this way, then the gas pushes up in the equal and opposite direction on the rocket. So when the rocket is in space in a vacuum where there's no other molecules in contact with it, if it pushes the gas downward, then the gas pushes the rocket upwards. So let's go ahead and label that. So basically what you're doing is if you were to write a little phrase that would describe what happens, you're always swapping the two objects and changing the direction. What I mean by that, it says rocket pushes gas downwards. So I'm switching the word rocket and gas and then changing the direction to show that it's an equal and opposite force. So the gas pushes the rocket upwards. Okay, so for Newton's third law, there is basically no cases at all where there's not another force pointing in the exact opposite direction. So if things are in contact, and although one thing might be bigger and one thing might be smaller, it wouldn't matter. So if you had a giant 100-kilogram object being pushed up against a 2-kilogram object, that force that they would feel between them would be exactly the same. So if the whole entire system is getting pushed, maybe the blue box feels a force going this way, and then the red one would feel one going this way. In the end, those would be equal and opposite. But if you want to find out what's going on, you just analyze just the forces acting on that particular object. And if you just focus on a single object, then it'll typically be a lot easier to predict what's going to happen. All right, so let's take a look at all the different types of forces, and we'll talk about some details and important concepts related to each of these different forces, and then how to include them in your diagrams. So we have a few common forces that you're going to see. We have force of gravity, which is basically going to be a free force that is the Earth pulling things towards its center of mass. So as far as we're concerned, it's just the Earth pulling everything directly straight down. So it doesn't matter if something is turned on an angle, it is a pull straight down from the Earth in every single case. The force of tension is from any rope like material, so anything like a rope or a string or a chain, and that is always some kind of pull as well. For an applied force, this one is one that if it doesn't fall in the force of tension category, it would be basically any kind of push or pull from someone or something. As long as it's not a rope-like material, then it won't fall in the category of the force of tension. So applied force is kind of like a larger category. For normal force, the word normal in this case means perpendicular. So it is a perpendicular, and I'll call it a perpendicular support force, but it's not necessarily always supporting an object. But if two things are in contact with each other, there is always a perpendicular force acting. But a lot of times it is from the actual surface itself. And our last one, we have two different ones. We have force of friction, kinetic, and then static. So the word static means at rest, and the word kinetic means in motion. So the one that people are most familiar with is the force of kinetic friction. So anytime things slide along the surface of each other, there is kinetic friction because of the irregularities that are inherently in all surfaces. It's kind of like the roughness of the surface is kind of scraping against each other. So even if it's something really smooth, it still has some irregularities. So there's still some really small bumps that are invisible to the naked eye that interact with each other. And as those go across each other, they provide a force that opposes the slide. So for these, we'll just basically say that these oppose a slide, and kinetic is opposing a slide of something that is actually moving, and then static is opposing a slide of something that is trying to move but it remains at rest. Now, the force of static friction is always greater than the force of kinetic friction. on the same surface. So when something is already in motion, and we'll kind of say it's cruising over those bumps, those irregularities in the surface, and it already has some inertia, it is going to be easier than something that is sitting at rest and sort of, we'll say, stuck in the little bumps and grooves of the surface. So the capacity that static friction has to push back against something is going to be greater than that of kinetic friction. So let's go ahead and take a look at our different force diagrams. So you may be drawing diagrams where you put vectors right on the actual objects, or you may be doing a free body diagram. So free body diagrams are exactly what they sound like. They're not including the actual body or object that you're looking at. All right, so if you take a look at this thing over here, we have a box that's suspended from a ceiling. So we have two rope-like things. Those things would be pulling. So we would have two FTs. You wouldn't just group them up and say we have one FT, because there are two different objects pulling on it. So there's two forces of tension, and then there is always a force of gravity pulling straight down. And it doesn't look like we have anything supporting it. So no normal force. There's no type of interaction between a surface of any sliding. So there is no friction involved. And then we just have FT and FG. So if we were making that a free body diagram, we would get rid of the object itself and then just put our forces on a single point, and then that would be our free body diagram right there. Okay, so depending on what you're choosing to do, you can draw the free body diagram off to the side, or you can draw the forces on the actual object, or you could do both if it helps you visually, just sort of help you figure out what's going on with this particular scenario. So let's take a look at this scenario. We have an object that is sliding down a ramp. Now we have the force of gravity straight down, as it always is. So although something is on an angle, it still has an FG straight down. And then it has a normal force because the surface is supporting it. That is perpendicular. So perpendicular creates a 90-degree angle. There's a 90-degree angle right there for our Fn. And then because the thing is moving and sliding, we have a force of kinetic friction that is opposing the slide. Again, if we want to do a free body diagram, we would just kind of draw a little dot off to the side and then connect these three forces to it. Now for our last one, we have a person, we'll say, pulling, and then the object is at rest. So if we were to draw the forces acting on the object, we have the force of gravity as usual, pulling straight down. We do have a surface supporting it, so we have a perpendicular force pushing up on it to keep the box from moving up and down. And then if it's being pulled, then we have a force that is an applied force. Like I said, that's sort of a general category. So if we have any push or pull by something or someone, and it's not the force of tension, we could probably go ahead and say it's an applied force. Now, if something's being pulled and it's trying to slide and it's not in motion, then there must be another force trying to oppose the slide, and something opposing the slide would be the force of static friction. So it is the irregularities in the surface interacting with the object that is pushing back in the opposite direction. And plus, if it's at rest and we have one force going to the left, then we definitely know that there has to be a force going to the right that would be canceling that force out. So that is the quick overview of all of our different forces and how to add them to each of the scenarios. Once you've had enough practice and experience taking a look at different scenarios, you won't have to necessarily scroll through all these forces, but you'll be able to identify them based on the things that are in contact with the object and also possibly not in contact. Generally, the only one that's not in contact is the Earth for the force of gravity. We're not going to be dealing with any magnetic forces or anything at this point. So most of the other things are because something is in contact with it and interacting with it and pushing or pulling it in some way. So with Newton's second law, it is basically the formula and ideas within the F net equals ma formula. So it's saying that the net force, the overall forces acting on the object, equals the mass times the acceleration, which shows you that the acceleration is proportional to the force and that the acceleration is proportional to the inverse of the mass, which is basically saying that acceleration is inversely proportional to the mass. Now, Newton's second law is the foundation of how a lot of the problem solving related to dynamics works. So let's take a look at a basic example first before we get into some more complicated ones. So when you're taking a look at something, you might have an object, and that object might be pushed to the right by a person. So we have an applied force. And because it's sliding, we have a force of kinetic friction opposing the force. And then we have the normal force perpendicular from the ground supporting the object. And then we also have the force of gravity pulling the object straight down. Now, the way you analyze it is along both of the axes. What I mean by that is you look at all of the forces in the horizontal direction and the vertical direction. Now, the thing is, they might all be pushing or pulling on the object at the same time, but the way that they interact with each other is a little bit different. So we want to make sure we just focus on the horizontal forces, which we'll call that the sum of the forces in the x direction, or we just focus on the sum of the forces in the y direction, which you might call F net x and F net y, but that's all the same thing. Now, what you want to do is if forces are working in the same direction, you add them up, and if they're working against each other, you're going to subtract them, and that is the net force in a particular direction that gives you the mass times the acceleration. Now, in the x direction, we have the applied force, and then in the opposite direction is the force of kinetic friction, so that equals the mass times acceleration. In the y direction, we have the normal force pushing it up, and then we have the force of gravity counteracting it, pulling it down, and that equals m times a. Now, if you're analyzing it to figure out what the actual acceleration of the object is, you wouldn't necessarily pay too much attention to this usually, because we know that it's not moving up and down. In fact, if it's sitting flat on the surface, then Fn minus Fg equals 0. We know that there's no acceleration in the vertical direction. Therefore, this whole entire side equals 0, so that Fn minus Fg would equal 0, and Fn would equal Fg if you added Fg to both sides. In the horizontal direction, we have Fa minus Ffk, and for that, you'd probably have to get some kind of value for each one of those. For the force of kinetic friction, you may use the coefficient of kinetic friction times the normal force to solve for that force of kinetic friction. In that case, the normal force that you would find over here would be pretty significant. And then from there, you might be finding an acceleration, applied force, a mass, just depends on the problem. Now, moving forward, there's a lot of different scenarios that are going to get way more complex than the one that we just previously saw. For example, if you have an object being pulled on an angle, so say, for example, there's maybe a force of tension pulling it up 30 degrees above the horizontal, and let's say that it's maybe not moving at all. So we have the force of static friction opposing the slide, and then in the vertical direction, we have the normal force as usual, perpendicular upwards from the surface, and then we have the force of gravity from the earth pulling it down. Now, in this case, what you want to do is if you have any angled components, you always break them up into their x and y components. So if we take our force of tension over here, and we'll just kind of create our own little triangle, you would break it up so that it has an x component, which we would call the ftx, and a vertical component, which we would maybe call an FTY. You can kind of label it whatever you want, but just so you can know the difference between the horizontal and vertical components. Now, if you use a little bit of trig, we can find the FTY side because it's opposite of our 30-degree angle. So we would say sine of 30 degrees equals the opposite, FTY, over the hypotenuse, which is our main force of tension. And then in the end, if you cross multiply this over, then Ft sine of 30 degrees would equal your y component. And then in a similar fashion, you would do the same thing for the Ftx, but since the Ftx is on the adjacent side in relation to our 30-degree angle, you would just end up doing ft cosine of 30 degrees to get your ftx. Let's go ahead and fix this y. And then you would go ahead and use those two components. Now in the vertical direction, it's going to look similar to our previous problem, but a little bit different. We know that we have two forces upwards. We have normal force, and then we have this force over here, which we call the Fty. So we have two positive ones because they're both upwards. So we'll say the normal force and the Fty are my combined forces in the positive upwards direction. And if you subtract Fg in the negative downwards direction, that would equal 0. We can safely assume that it's 0 because there is no motion in the vertical direction, therefore there is no acceleration. And then in the horizontal direction, remember we have this component over here, which we'd call our Ftx. So if you summed up all the forces in the x direction, then you would say we have an Ftx minus the force of static friction. And then in this particular case, we can also say that it's equal to 0 newtons because the scenario that I gave you was that it was being pulled but remained at rest. That's why it's static, and that static friction is opposing the slide. So in that case, you can also safely assume that it's 0. And then for your force of static friction, you would use the coefficient of static friction times the normal force to get that potentially. And then you would make sure you use some of our previous work like this over here and this over here. So if you were just given that Ft using your sine and cosine functions, we can go ahead and do a little bit more work to find the exact values for Fty and Ftx. And then obviously, depending on the problem, you're going to do some algebra and then solve for your unknown variable from there. Now let's go ahead and analyze an object on a ramp or on an inclined plane, which is a common scenario that's often analyzed in dynamics. And this one is going to work a little bit differently because we will not have an x and y axis that is perfectly horizontal or perfectly vertical. Because we're on a ramp, we won't have any motion in the horizontal or vertical direction. We would have it in the parallel or perpendicular direction. So we can kind of make a new x and y axis, and then we can call this the parallel direction, and then we can call this one the perpendicular direction. If you still want to call it the x and y, that's fine too. It's just sort of like a tilted axis. So what you want to do is you want to make sure all your forces are along this orange dashed line or along this green dashed line. And then that way we can place it into our x and y formulas when we create our formulas a little bit later after we draw our forces. Now, if we're drawing a diagram here, we have Fg straight down as usual. And we would be given some angle theta over here for the amount of incline for the particular ramp. And then we would have the normal force that it is pushing up perpendicular from the surface of the ramp. And then if it's just sliding down from the force of gravity, then that's all we have unless there is friction between the ramp and the block. So we'll say that there is. In that case, we will go ahead and say that we have the force of kinetic friction opposing the slide. Now what we want to do is our Fg is falling in between the orange and green dashed line. So we don't like that. We want it perfectly along this axis, the perpendicular direction or the parallel direction. So what we're going to do is we're going to take a component of it that pushes down perpendicular into the ramp, and we can call that Fgy. And then we'll take the parallel component this way and we'll call it Fgx. Now it turns out that this theta over here always translates to this angle over here. And what we can do is same thing we did earlier. We could use a little bit of trig to find our different components. Now, if you take a look at our theta here, the opposite end of it is our Fgx. So our Fgx is going to equal Fg sine of theta, which is a little bit different than last time because we used the sine of the angle to find the vertical component last time. Now we're using it to find our parallel or x component. And then for the perpendicular component, we are going to use FG cosine of theta because that is the adjacent side to our angle. And again, these are some more specifics so that if you were to find the FG by doing mg, mass times 9.8, and they just provided the mass, then you would be able to do a little bit of math over here and then find your FGX and your FGY values. So if we were to set this one up, we would maybe have the sum of the forces in the perpendicular or y direction. And then for that one, we have the normal force pushing up. We have our FGY downwards, and again, we can safely say that equals 0 because there is no acceleration along this axis over here, along this orange dashed line. And then for the sum of forces in the x direction or the parallel direction, we have FGX that's sending it down the ramp, and then we have the force of kinetic friction that is opposing it. And in that case, we would very likely have an acceleration. So we would have to set that equal to m times a, and then we would either solve for an acceleration or plug one in to find another variable. And again, we may use this formula over here, coefficient of kinetic friction times normal force for our force of static friction, or excuse me, our force of kinetic friction. And then for our FGY, if we wanted this, then we would make sure that we use our work that we set up previously over here. And then if we wanted our FGX, then we would make sure we use this little formula over here. Okay. And again, it all depends on what you're looking for, but that's the general setup and idea of working with an inclined plane. All right. The last type of problem we're going to take a look at is taking a look at some pulleys or a system of objects that may be accelerating together. Now, the method behind these is all fairly similar. You might have something called mass 1 and mass 2. And then if you were to draw the forces acting on them, you would have something like this. You would have the Fg from mass 1. You would have a force of tension from the rope. We'll call it Ft1. And then similar type values for our second one, which we would have an Fg on this one, which we can call Fg2, and then a force of tension from this one, Ft2. Now, the trick to these is basically setting up three formulas, one specifically for M1, one specifically for M2, and then one for the entire system. Okay, so let's just take a look at each specific system first, because that's maybe what we're a little bit more accustomed to. So if we take a look at this first scenario here, we don't have to work along the x-axis for either of them. Everything is going to be vertical, which is nice for us because it'll exclude a little bit of the work. So we have the sum of the forces for mass 2. Now, what we're going to do for this one is, because pulleys just redirect the force, we want to make sure we figure out what our positive and negative direction is. Now, if M1 is greater than M2, it's pretty safe to assume that M1 is going to win the tug of war between these two objects, and everything is going to move up and around this way. Okay, so we could say that everything that is propelling it in that direction is in the positive direction. So we call everything that's going around in this direction in the positive direction, and everything that's going in the exact opposite direction of that, that is going to be the negative direction. So for M2, we have our Ft2 minus our Fg2, and that equals the mass times acceleration for M2. And then similarly, for the sum of forces for mass 1, we have the same thing, but Fg1, remember, is in this direction of how everything flows. So Fg1, although it's downwards, we're going to call that positive in this particular scenario. And then we have that Ft1 counteracting it, and that equals Ma. We'll call that M1A. Now, if you take a look at the entire system, you're going to do something like this. It would look Okay, something kind of like that. So that's not a great picture, but it's just this big blob that includes both of the masses, the string and the pulley. We're just going to assume the only thing with significant mass are the two blocks. So anything that is internal in our system is not going to count for our forces, because there's all kinds of internal forces acting within systems and objects, and those we are not going to concern ourselves with because it's not going to affect the overall acceleration of the system or the object. So the sum of the forces for the whole system is just going to be FG1. See, this is external. This is sticking outside of our big blob, FG1. And then the only other one that's sticking out is FG2. And that is equal to the mass of the entire system, M1 plus M2 times A. Now, oftentimes what you can do with that is you're going to want to solve for the A, whatever number that is, first. Okay, not in all scenarios, but in a lot of them, you're going to solve for the acceleration first, and that is going to be the same acceleration for each of those formulas up top, and then you can solve for a lot from there. So if you're given the masses, or you maybe just keep them in variable form, you have a bunch more to work with if you solve for the acceleration here as a total system and then plug it back into those. Again, it all depends on the scenario in which you're working with, but you're going to want to solve for everything as a whole system and individual pieces for a lot of these. So I'm not going to completely cover all the other ones, but let's go ahead and take a look at them. We might have something like an M1 and an M2 for the rest of these. And again, you would look at them individually and separately. So for this one, if we draw in the forces, we would have the force of gravity, normal force, force of tension, we'll call it FT2, and then we may or may not have friction here depending on the scenario. We're assuming that is going to slide, so we have an FFK. And then for our second one, we have an FG, call it FG1, and then this FG2, since this is mass 2. And then this one has an FT, and we'll call that FT1. Okay. Again, we can set up separate formulas for each one of these, and everything is going to be flowing in a certain direction, which is in this direction. Okay, so that would be considered positive. So if we took a look at our entire system for this one, it would basically just be, let's go ahead and wrap our system up to specifically define what it is. And you could see that all of the forces are internal. This Fn would be sticking out. It just kind of ran out of room, and this Fg2 would be sticking out. But those two are canceling each other and not along the direction of the motion anyways, which would be over and then down. So what you would do is you would say that we have an Fg1 minus the FFK up above in purple, and that equals both of the masses combined times the acceleration. And again, if you wanted those individual formulas like we have in orange and blue over here, it would basically just be the FT2 minus the FFK, and that would equal M2A. And then for our M1, it would be FG1 minus FT1 equals M1A. Okay, again, it's all based off the same idea of this main problem that we worked out over here that's in orange, blue, and purple. Now for our last one, again, it's sort of a similar idea where we would have maybe an applied force here, normal force here, force of gravity, and then let's say this case would be frictionless, then we would have this FT tugging M1 backwards. And then for our second one, we would have this force of tension tugging M2 forwards. And then same thing as the first one, we'd have a normal force and a force of gravity. So you can do an individual X and Y formulas for M2 and M1 as we did earlier, so I'm not going to repeat that process. But then again, you can treat it like one giant object and then pretend that M1 and M2 are one big system. Okay, in that case, we have these two vertical ones that are canceling each other out, these two vertical ones that are canceling each other out. So then in this case, that FA would just equal M1 plus M2 times the acceleration. And then if there was a force of kinetic friction, that would be the opposing force that you would subtract from the applied force. Okay, so main takeaways from this is that you want to make sure you define your system and which direction is your positive or negative. Okay, so the positive is the way that everything is going to flow based on what your scenario looks like, which might change if up or down is positive or negative, or left or right is positive and negative. And then once you have that system defined, you can analyze the system as a whole with the main external forces that are propelling it and opposing the motion. And then that m times a, remember, is going to be the sum of all the masses involved times that acceleration. And then you're going to want to have most likely some individual formulas for your individual objects. In that case, you would ignore your system and pay attention to each of those masses individually and create individual formulas for them, just as I did in orange and blue over here. All right, now two more topics that I want to finish off with, both of which don't have a lot of detail in this overview, but I'll give you a few important points. Now we have something that's related to springs, which is Hooke's law, which we have the force of the spring equals kx. A couple things to know about that is that your k is your spring constant. And it's basically just telling you how stiff or stretchy your spring is. It is how many newtons of force are required to stretch it 1 meter. That's why it's the unit is newtons per meter. So a lot of times, if you don't understand something, if you analyze the units, it may help you a lot in the concept of what it is. So it's the amount of force required to stretch it 1 meter. Now for the second one, our x is basically a displacement in meters. Okay, but it's the displacement of how much it is stretched or compressed. And we'll say from equilibrium. Okay, and by from equilibrium, basically what I mean is what is the length of the spring when it's not being affected by any outside forces. So if the spring is sitting at rest and it's 1 meter and it gets pulled to 1.2, then it's only stretched 0.2. So say, for example, this change in its position is 0.2 meters because it was originally 1 and then got stretched to a total of 1.2, then our delta x is 0.2. There is a negative here because the force of the spring is a restoring force. It's a restorative force, which means that if you're stretching it out this way in the positive direction, it's actually pulling back in this direction, and then vice versa. For a compression is that your delta x would go in the other direction, in the negative direction, and then it would be compressing it and pushing it out in the opposite direction. So there's not too much to that. You may use some of those details and ideas when analyzing springs and taking a look at those formulas. Lastly, when we're taking a look at kinematics and Newton's second law, there's a lot of connections between the two, but mathematically, this is the main one. So if you're taking a look at the sum of forces equal to mass times acceleration, mass wasn't mentioned a whole lot during kinematics, but acceleration is that connecting piece to where if you are looking for an acceleration, you may find it in one of these formulas. So because the main problem solving method is using second law and taking the sum of forces and setting equal to mass times acceleration. In certain cases, you may connect that to kinematics and your three kinematic formulas because they all have an A in them. So one of those A's might be an acceleration that you plug into your acceleration over here, and then possibly work backwards from there. We're going to be analyzing two problems with a bunch of forces acting on them, and then we're going to be solving for the acceleration. The first one, we're going to be using all numerical values to talk about the concepts and problem-solving process. In the second one, we're going to solve it in terms of all the variables and how those concepts and all that algebra works. So for our first one, we have an applied force of 80 newtons directed in the downward left position or direction. And the first thing you always want to do is start off with your free body diagram and draw your forces. I'm going to draw them right on my box though. So we of course have Fg pulling straight down from the earth. We have a normal force pushing up from the ground perpendicular to the surface, supporting it. We have this applied force already, so I'll just kind of leave that one there. And then we have a mu sub k, so we definitely have some friction opposing the slide in this direction. All right, now anything that doesn't fit perfectly along your vertical or horizontal axis, you want to make sure you put some components with it. So my applied force is obviously on an angle. It's not vertical or horizontal. It's a little bit of both. We have a vertical and horizontal component to this one, which I'll call FAX, and then we'll call this one FAY. Okay, now that's not actually part of my forces, those are just pieces of my FA. Now what I want to do is analyze each of the axes separately. So I'm going to take a look at the sum of the forces in the x direction, which is also known as the F net x. Now in the x direction, I have something called an FA, just the x component pushing it to the left. I'll call that my positive, and then I'll say my force of kinetic friction is opposing the slide. Whoops, I'll put that F over there. And we know that our net force is always equal to m times A. Secondly, we have the sum of forces in the y direction. And this one, if I'm taking a look at it, I have two of them going down, my FAY and my FG, and then I have my FN going up. So I normally say everything up is positive, everything down is negative. So FN is my positive minus my FG minus my FAY. Okay, and that one is going to equal m times A2, but I know that's going to be equal to 0 newtons because in this particular scenario, there is no movement or acceleration in the vertical direction, so I'll just call that 0. All right, now my ultimate goal is to find this acceleration right over here. So let's go ahead and plug in some numbers. Now I have FAX that I want to plug in, and I want to plug in FFK. If I want FFK, I know that I want mu times the normal force there. So I already have mu in my givens, it's 0.1, and the only way to find normal force is to find it right over here. So I know I want to solve for that at some point. My FAX is going to be pretty easy because I have the hypotenuse of my triangle, which is 80, and I have an angle of 20 degrees to work with, so I'm feeling pretty good about that. So if I want the vertical component, I'm going to use sine because it's opposite of my theta. So sine of 20 degrees equals the opposite end, the FAY, over the hypotenuse, where the hypotenuse is 80. Okay, so I'm basically going to multiply 80 on both sides. 80 times sine of 20 is going to give me my FAY, which is 27.36 newtons if I round it to the hundredths place. Similarly, for my x, I want the adjacent side to my theta. That one I'm going to use cosine of 20 degrees and that's equal to my FAX over the hypotenuse as well. I know the hypotenuse is that 80 Newton force that they originally gave me. Same thing, multiply both sides by 80. 80 times cosine of 20 is going to give me 75.18 newtons. All right, so that's a bunch of useful stuff that I'm definitely going to need. This force right over here and this one over here. All right, so now I'm ready to go. Let's go ahead and start plugging in some more numbers. We have 75.18 over here, and then we have 27.36 over here. Okay, I know my FG, we can always get that by mg, which is mass times 9.8. That one I can do in my head because the mass is 10, and 10 times 9.8 is just 98. So that one worked out pretty nicely for me there. And now it looks like I'm in pretty good shape because I have everything except my Fn. So I'm going to solve for my Fn by adding 98 and 27.36 to the other side. And then I got 125.36 newtons. Okay, now remember, Fn isn't equivalent to Fg in all cases if there's some other vertical forces. If it was just sitting at rest, then our Fn would be equal to Fg, but since I have a little downward force shoving it into the ground along with the Fg, the Fn has to be able to counteract both of those, so that 125.36 is obviously bigger than my 98 from the Fg. All right, now going up to my top part, I have mu k, which is 0.1, the coefficient of kinetic friction, times my normal force. And that's going to allow me to get my net force. All right, so let's scoot this over a little bit. And I have my FAX minus the product of my 0.1 times 125.36. And that gives me a net force of 62.644 newtons. Okay, that net force, I can go ahead and set that equal to MA. And my M was 10 kilograms, and got that and the other side, so I'm going to go ahead and just divide both sides by 10. And then now we have a final A value of, I'll round it to 6.26 meters per second squared. All right, so recap. Number one, you for sure want to do your force diagram or your free body diagram. From there, when you do the sum of forces in the x direction and the sum of forces in the y direction, only things that are horizontal go in the sum of forces in the x, only things that are vertical go into this one. So since we have an angled component, you basically close it off into a right triangle, so you have a vertical and horizontal component. And then from there, you place all your forces into a formula. Oftentimes one of them is equal to 0. This one we had a 0 right over here because we have no motion or acceleration in the vertical direction. So now I'm focusing on my sum of forces in the x direction and looking for everything I need. I found this FAX right over here by doing a little bit of trig. And then I found my mu k times Fn by, well, I already knew my mu sub k. And then my Fn, I had to use my sum of forces in the y to get that value. From there, I was able to get to my final setup, which is the net force equals m times a. And then from there, some basic algebra, dividing both sides by 10 and getting my final acceleration of 6.26 meters per second squared. Okay, obviously not every question is asking for the acceleration, but you basically fill in as many numbers as you can and then work your way towards the solution. Now for our second problem, we're going to be looking at a scenario where someone is pushing a block up an incline, and we're going to solve for the acceleration in terms of mu sub k, fp, mb, and g. This one is going to be a little bit more complex than the first one, and it's focused more on the concepts and knowing your trig and algebra as well. All right, so if we go ahead and draw a free body diagram, we have the FG straight down. We have the person pushing it up the ramp. which is known as the force of their push. You could probably call that an FA, an applied force as well too. And then you also have a normal force perpendicular to the ramp. And because it's getting pushed up the ramp, then we're going to have kinetic friction opposing the slide. Now, for anything that's on an incline or decline has a unique characteristic, which is it has to be analyzed on two different axes that are tilted. So we have a horizontal and a vertical axis. The horizontal one is now known as the parallel axis, and the vertical one is now known as the perpendicular axis, because all the forces are going to be operating perpendicular or parallel to the surface. So you're basically taking your x-axis and your y-axis and then tilting it to match up what's going on with the ramp. Now, the same rules as before. After you draw your free body diagram, we want to make sure all our forces fit along the x and y axis. All my blue vectors finish up my force diagram, but now I have an FG that's actually not fitting along one of my axes. So I want to give it a perpendicular and parallel component, which I'll call FGY and FGX. Okay, now I have everything sitting along my new x and y axes. So for all of my forces that are along the x direction or parallel, whichever one you want to call it, we have the force of the push that is propelling it forward, and then we have the force of kinetic friction that's opposing that slide, and that's equal to m times a as usual. And then we also have the sum of the forces in the y direction, also known as the perpendicular direction for this ramp. We have our Fn going upwards on the ramp, and then we have our Fgy going downwards on the ramp. And that one is going to be equal m times a, but I know that's going to be 0 newtons, so because there's no motion that is perpendicular to the ramp. Okay, actually I noticed I made a mistake in the first part. We have Fp minus Ffk, and then also I forgot to subtract my Fgx, because that's going down the ramp as well. All right, so I got all my horizontal forces, all my vertical ones, and now we're ready to go with doing some substitution. So we know we eventually want to solve for the acceleration, so we're going to have to do a little bit of trig and moving stuff around as well. Now, if you want everything in terms of these four things, I want to make sure I'm strategic in working those out so that we have an answer that's in terms of those four unknown variables. So we have Fp, this one's good, we can kind of leave it as is. We have Ffk, which is going to be mu times the normal force, okay? Mu actually works because that's one of our variables that we want in terms of, but Fn, we're going to have to find some way to substitute that out. And then same thing for our Fgx. All right, so now we're thinking we have this right triangle over here, our Fg triangle with an Fgy and Fgx. Now, our angle theta over here actually translates over here to being the theta over here. Now, if we use that, if we were to use the numbers, again, we're going to use sine and cosine, and Fg as our hypotenuse. So if you look opposite of theta, that's where my Fgx is at. So Fgx ends up being Fg sine theta, which we're going to rewrite as mg sine theta, because we know Fg is mg. And then also similarly in the y direction. Now in the y direction, you can kind of see over here, theta is, or Fgy is adjacent to the theta. So we have Fg times cosine of theta to get that adjacent side, which then ends up being mg cosine theta. All right, so now we like that because it gives us more things in terms of the variables that they gave us. So we can write our FP as it is, because that's one of the terms they allowed us to use. We can write our FGX now as mg sine theta. Over here, we still want to keep this ma as it is, and then this side, we want it to be mu times normal force. Okay, here's the thing. We can't use Fn as part of our answer. So we're going to find Fn. We see it right over here in our sum of forces in the y direction. And we do actually know Fgy with our little bit of trig work over here. So Fn minus Fgy equals 0, which would mean Fn equals mg cosine of theta. Okay, we're going to take that and then substitute it in right over there. All right, so let's go ahead and clear out a little bit of room and then do the last bit of rearranging to solve for A. All right, now in green, I made all my substitutions. I got the FP here, the mu sub k with my mg cosine theta that we just talked about, which is my Fn that was equivalent to my Fgy. And then I have my Fgx as mg sine theta. So to solve for A, all I have to do is divide both sides by m. So take this entire thing and then put it over m. So double check. I have everything in terms of Fp. I got that in the beginning. Mu sub k, it's in there once. And then I have my mass and my g. I can put the little subscript for the b next to the m's for just mass of the box. Either way, it's the same thing. All right, so when doing this kind of problem, again, it's pretty similar to what we did with the previous one. You start with your forces and you analyze those vectors to see if it's along your x and y axis. Your x and y axis is typically just completely vertical or completely horizontal. If something's on an incline or decline, then you go parallel and perpendicular, just like the case we're looking at now. Then you analyze any vectors that fall in between those axes. In this case, our FG did fall in between our parallel and perpendicular. In that case, you close off a little right triangle to get a vertical and horizontal component. So that when you do sum of forces in the x and y, you can place all of those vectors in their proper category. From there, you do some trig, some algebra, kind of expanding things out as much as possible. This one, we had a specific goal of solving stuff in terms of 4 different variables, so we know we needed to do a little bit of trig before we did some algebra, and we were able to solve for A. So that's the problem-solving method. If you saw both of those two examples, the approach of it was pretty similar. So you have to be pretty methodical about setting up your diagram, your sum of forces in each of the axes, expanding out to different formulas, plugging in numbers, and then hopefully you'll find your solution. So I hope that was helpful to you in mastering the force problem-solving process. Thanks for watching and listening.